right, a 75-kilogram firefighter climbs a flight of stairs 10 meters high. How much work is required? All right, so here's our stairs. Here's our little firefighter person. That's 10 meters. Okay, so work, of course, is force times distance times cosine of theta. He's going to travel a distance of 10 meters, which means that our displacement vector is pointing up. Now we have to figure out which force is the one that's going to do the work, right? And the question says how much work is required, meaning how much work is required to get up the stairs, right? So if I draw a free body diagram, then I know that there's a force of gravity pulling down on the firefighter, right? But is that the force that's going to do work here? No. The firefighter is going to have to push against the stairs, right, to overcome his own weight and move up the stairs. So that means he's going to have an applied force that's going to be equal to his weight. He has to lift his own weight to get up the stairs. So that means we're going to have this, and that work is going to be because of that applied force. That means the force vector that's doing the work is pointing up. So what's the angle theta between that? 0. Okay, so the force applied is overcoming the force of gravity, so that's going to be mg times d. What's the cosine of 0? 1, so that part we can leave off. And all right, so it says 75 kilograms times 9.81 meters per second squared times 10 meters. Y'all plug that in your calculator and let's get an answer. How many sig figs should you have?
3.
3. Very good.
I didn't know it was 5 minutes.
I didn't know force of gravity. Force of gravity is mg, and this is equal out. Okay.
Zero going opposite of just be 180. Like,
Yeah, well, if he would, the displacement vector is pointing up. Yeah, so if the force vector was the opposite direction, then yeah, that'd be 1.
but if they're going the same way,
Then 0.
Okay.
All right, what do we got?
7,260.
All right, very good. Questions? Okay. All right, so a 900 Newton, and since it's giving me units of newtons, is that mass or is that weight?
That's what.
Weight, very good, okay? So this 900 Newton weight crate is resting on the floor. How much work is required to move it at a constant speed 6 meters along the floor against a friction force of 180 newtons? Alright, so if we're going to move it, that means we're going to have to apply a force to it. It said a constant speed, which means that there's no acceleration against a frictional force. So if I do my free body diagram, I'm going to ignore the y-axis because it's not moving in the y-axis. So that gives me this as my free body diagram. And then I'm going to do my F-net statements. So what's the first one?
F net y equals number, or x. And something.
Okay, mass times acceleration, the x-axis. Since it's a constant speed, what does this equal? 0 newtons. Alright, F-net in the x-axis also equals what?
Force of gravity is force of
set those equal to each other, which means that the force applied is going to end up equaling the force of friction, right? They gave me a value for the force of friction of 180 newtons. That means that this force applied here has to be equal to 180 newtons. Work is equal to force times displacement times cosine of theta. The force that's going to cause the work this time is the applied force. So we have a force vector in this direction, and we have a displacement vector in that direction. So what's the angle between them?
0.
Okay, so what's this going to become? 1. So that means we've got 180 newtons times, it's going to move 6 meters. So plug that in. How many sig figs should you tell me? 2. Okay, so what do you get?
1,100.
That's a naked number.
1,100 joules.
There you go. Alright. That makes sense to everybody? Just plugging in this standard work formula. Okay, then the next one, letter B, says, alright, well what if you want to move it 6 meters vertically? Okay? So, again, work equals force times displacement times the cosine of theta. Okay? Now, we're still going to have the work being done by an applied force, except this time, the person's going to try and lift it up, right? So applied force is going to go up. It's a 900 Newton box, which means that the force of gravity acting downward is 900 Newtons. So if somebody is going to lift it up, they have to overcome the 900 Newtons, right? So that means that the force applied has to be 900 Newtons, okay? So, that means that our force vector is going up. They're lifting the box in that direction, so our displacement vector is going up. So the work done then is 900 newtons times 6 meters vertically. And then what's the angle here? 0, so that goes to 1 again. So what do we get this time?
5,400 joules.
Everybody agree with that?
On 2A, why do we have to do F in that statement?
So that we could understand that the force applied was going to be equal to the force of friction. Yeah. Good. Other questions? Okay. This one's like pretty much the same. We can look at it. How much work did the movers do horizontally pushing a 150 kilogram crate 12.3 meters across a rough floor without acceleration if the coefficient of kinetic friction is 0.70? Okay? So if I have, again, some crate that I need to push along and my coefficient of friction equals 0.70, that means there's going to be a frictional force in this direction. So let's see, work equals force times d times cosine theta. My displacement vector is going to be in this direction, because that's the way I'm moving it. Alright? Now, we know that the acceleration here is going to be 0, and I need to know what my net force is going to be that's going to cause the box to move forward, right? So I need to do some F net statements. So I'm going to have force applied, and I'm going to have that frictional force over here. And there's no acceleration in the x-axis, means they must be pushing at a constant velocity. So what can you say about these two things then? They must be equal. So the force applied must be equal to the force of friction, which we know is also equal to the coefficient of friction times the normal force. So I have a force of gravity here. I have a normal force here. There's no acceleration in the y-axis. So what can you say about normal force and gravity? They must be equal. We know that force of gravity has its own formula, which is mg. So that means this must be equal to the coefficient of friction times m times g. So all of this right here is the force applied, all right, which is the thing that's going to do the work. Okay, so I can say then that coefficient of friction times mass times little g times d. Now cosine of theta, our force vector is this way, our displacement vector is that way. So what's this? 0. So that's going to become 1. So that's good. We can say 0.70 times, what was the mass? 150 times 9.81 meters per second squared times, it's going to move 12.3 meters. Alright, how many sig figs should we have? 2. Alright, so plug that in and let's get an answer. Okay, what do we come up with?
13,000.
What?
Wait, how many?
Yeah,
Well, that's a good question. How many sig figs?
13,000.
2. Alright.
13,000.
I mean, if this test is
No, we're in the easy.
yeah, I mean, like, you're probably not going to ask any questions from the first 2 pages. I'm feeling confident reading.
Never know. Alright, so hopefully that's pretty easy. Number 4 is on an inclined plane. Okay? So, do we want to look at that one, or do you
Yes.
think you got it?
Yeah.
No,
We do? Okay.
I thought you said dolphins.
Okay, so some sort of a piano is going to slide 4.3 meters down. An incline that is 30 degrees. And it's kept from accelerating by a man who's pushing back on it parallel to the incline. Coefficient of friction is 0.4. Okay, so normally here, obviously I'm going to have my force of gravity. Since there's friction and this has an inclination to move this way, that means that I'm going to have a frictional force that way. It would normally also have a force down the plane, and now some guy is going to push on it, right? Which means there's also an applied force in that direction. And then, as always, normal force. Okay? So, letter A, calculate the force exerted by the man, the applied force. We're going to tilt our axis as usual. So that means that this is the x-axis, so let's look at that. I've got a force down the plane in this direction. I have the frictional force and I have the applied force in that direction. And it says that it is kept from accelerating, means the acceleration is 0, right? Okay? So what can you say about these then?
They're equal.
They must be equal, right? So let's see here. The force applied plus the frictional force must be equal to the force down the plane. And I want to know what that is. So what am I going to do? Subtract that over. So force applied equals the force down the plane minus the frictional force. Now what? Expand, right? So force applied equals, what's the formula for force down the plane?
Mg
G times sine theta.
G sine theta. What's the formula for friction? U times normal force. What's the normal force on an incline?
Cosine Ng.
Mg cosine theta, right? So we're going to say that that is mu k times mg cosine theta. That's the formula for normal force on an inclined plane. Okay, so you should be able to plug stuff in, so do that, and let's get this force, please.
Sine theta is the angle between displacement and
Okay, that's a good misconception we need to talk about, okay? This theta right here and right here is coming from our known force equations, okay? They're asking about a force. They're not asking about work right now, okay? This is about a force. So this isn't the angle between a force and displacement. That's not what that is. This is the angle of incline, okay? If you need to put like a little I next to this theta so that you remember that that's angle of incline, by all means do so. That is not a work theta. Don't forget your order of operations here. You need to do this normal force stuff first and then multiply by the coefficient of friction. When you do that. And then do your subtraction. Who's got a number for me? And how many sig figs should you be telling me?
But isn't
Who's got it?
420?
Very good. That's the naked number.
Oh, newtons.
Very good. Alright, 420 newtons, okay? That is letter A. I swear I didn't plan that. Wow. Alright, now, letter B says, what's the work done by the man on the piano? That means, what's the work done by the applied force? So, work done by the applied force is that force times the displacement times the cosine of theta. Now, this theta is a work theta, right? That means the angle between the force and the displacement vector, right? So, the applied force vector goes like this, but the piano, it says, is going to slide down an incline. It means it's going to go like that, right? So what's the angle theta between them? 180, okay? So, are you going to use the rounded 420 number right here? No, we need the big long number, okay? So, plug that in. How far is it going to slide?
4.3 meters.
4.3 meters. And then cosine of theta, what's that going to become? Negative 1. So we know our answer is going to be negative. And again, how many sig figs should we have? 2.
It's always when we get to the test.
Okay, what's the answer?
Negative 1800
Alright. So Saad says negative 1800 joules. Y'all agree?
Sir.
Alright, letter C. The work done by the frictional force. Alright,
Wait,
so,
was it negative again?
Hmm?
Oh, negative.
okay, so if we want the work done by the frictional force, then that's going to be the frictional force times d times cosine theta. Okay. You should also remember from your energy section that the work done by a resistive force is equal to the change in mechanical energy. So if you wanted to go about this from an energy perspective, you could totally do that as well. But I'm going to use this top one. Okay? So friction, that's this stuff right here, right? So go figure out what that is, just that, and put that here. And then of course the object, the piano, is still going to move the 4.3 meters. Now this angle here, friction also points this way. The piano is going to move that way, so what's this theta going to be? 180, so we know that, again, we're going to get a negative answer. Which is correct because the work done by a resistive force should always be negative. Yeah. Yep.
Thank you, sir.
Alright, Tim, what'd you get?
4100. Negative 4100.
That's a naked number.
Joules.
Good. Anybody else get that? Alright. Okay. Letter D, the work done by the force of gravity. Okay, so this is a little bit of a fun one here, alright? You have to pay attention to your angles on this. If I go ahead and extend my x and y axis, okay, so like that's x-axis, that's y-axis, okay, then that means that this right here, this is the vector that's parallel to my displacement vector, right? Okay? This is a 90-degree angle. This angle up here, we hopefully remember, is the 30-degree angle at the top of that triangle. What's this? 60. That means that here's my force of gravity angle pointing down. Here's the displacement vector. The angle between those two is 60, not 30. Okay? So watch out for that. Alright, so that means it's going to be the work caused by gravity equals the force of gravity times d times the cosine of theta, which we just said is 60 degrees. Gravity is mg, so that's the 280, 9.1. How many sig figs should your answer have? 2.
Why do you have to do all that to get the new angle?
Because by definition, this angle is the angle between the force and the displacement vector. And up here, that's 30 degrees. That's not the angle between the force and the displacement vector. That'd be the angle between like the force vector and the normal force or something.
Okay.
Can you explain how you got that angle and the new angle?
Yeah, when you draw in your triangle here on the force of gravity vector, the angle at the top of the triangle is always the same as the angle of incline. So, and this is a 90 degrees over here, that means this has to be 60 right here. This vector right here is the same as the displacement vector of the piano, so the angle between the force vector and the displacement vector has to be that 60 degrees.
Okay.
So, could you say it's always just going to be the same as the top angle?
Well, it's not. That top angle's 30 degrees,
Well,
so
no,
that'll match this.
The big triangle itself.
The big triangle. This
The ori-
one? Or
The
what?
original triangle, the one down the slope, could you say it's just the same as that angle?
I don't know what you're talking about.
Like,
Okay, so we have with this angle right here, I don't need a marker.
Wow.
Could you just say,
Wow.
so we said that that's the 60. Could we not just say that the angle is just the same as this one?
Yeah, well,
In this case, yes, of course that's true. But what if? Well, no, that's still the angle between. I think you could. Yeah.
Wait,
Okay.
so is that angle also one top angle?
What angle?
Yeah.
That's what I just asked.
I know. Is this angle always gonna be that angle?
Yes. Okay. So can I get an answer for that?
5,900 joules.
Okay. 5,900 joules. Was there another one? Yeah. Okay, so the net work done on the piano. So you have two options here. You can find the net force on the piano and then plug that into your work formula, or you can add up all of the works done on that you've already found, and that's the net work. When you do that though, are you going to use the rounded numbers? No, you can use your unrounded numbers. But you've already found all of the works, the individual works, so you can just add those and that gives you your net work. Alright? So go ahead and come up with an answer for me on that. I think I left that one off my key. Yes, sir.
0.
Okay, so Tim says that there's 0 net work done. Raise your hand if you agree.
Just because it's
And just because it's 10. Yeah, you agree? Okay, so our net work then is equal to the sum of all of the works, or it's equal to the net force times d times cosine of theta. And in this case, it equals 0 joules.
I didn't get 0.
No? What'd you get?
I got 421.
420.
I got 421.
What did you add together?
I mean, I added all 4 of the answers we have so far.
There's not 4. This is a force.
And that one's all?
Oh, yeah. That's,
Is there a way to solve this without adding up? I feel like say we had our friction one wrong, then we don't want to use that.
Yeah, you would need to go find your net force. So you would do your free body diagram, figure out what the net force is equal to, and then do your work formula with the net force in there. All right. Other questions? All right, let's move on. Okay, so force versus displacement graphs, right? What's the area under the curve going to be? Oh,
awesome.
it is a force versus displacement. I wonder what formula has force and displacement in
Oh,
it.
power.
Oh, dear God. That's right. Work, like the one we've been using.
Okay, that makes
Yeah.
sense.
Okay. Yikes.
Power?
Okay, so let's review area, right? Base times height. If I take the base, which is displacement, and I multiply by the height, which is force, that's F times D, right? What does that equal? Work. So the area of each of these things would be the work, all right? So you take a second, please, and I want to know how much work is done from 0 to 10 meters, and then again from 0 to 15 meters, okay? You could split that trapezoid into 2 triangles and a rectangle, or the area of the trapezoid is, what, 1/2,
1/2 height
Times
times 1
the-
plus B2.
yeah, base 1 plus B2 times the height.
Aren't the B1 plus B2 and they're on separate parentheses?
Or, okay. This is
stupid every time. Like, now, your sig figs, as you're looking at this, where are you pulling your numbers from?
The graph.
The graph. How many sig figs minimum, like which number has a minimum sig figs on either axis of the graph? What is it? 1. That means that your answer for both A and B is going to have 1 sig fig. Oh, I did. Alright, you got it? Or at least the letter A? Yeah, okay, so what's the work done from 0 to 10? 3,000 joules.
Alright, so we're saying letter A is 3,000 joules. Y'all agree? Yep. And since that's above the 0 line, this is a positive work done. Okay? Now, letter B wants from 0 all the way to 15, right? So, since this is above and this is below, what do you think you'll do to find out the total net work done? Subtract, right? You already know this one. Figure out that one. Subtract.
It's like, it's 0.5. Oh. Seriously? It's halfway.
What'd you get?
2,000 joules.
Okay, so it says 2,000 joules. Anybody else agree with that?
4,000.
Okay, Michael says 4,000. What do you say?
2,000.
2,000? Taylor, I know you got it.
1,000.
You get
It's only, I'm just doing it.
I'll tell you on this.
13 seconds.
For the Clemson.
Wouldn't you
yeah,
just be
this one
negative
right
though?
here equals the area of this.
No, but if you do
I
that,
definitely
your
got
height's
that.
a negative. So it should be kind of negative.
It's,
Come on,
I'm
Dave.
always wrong, I swear.
Size, right, this one's 2,000.
Okay. 5 plus 11.5 is 16.5.
So the one below, when I did my math, I got negative 700 joules.
Yes.
Okay?
Yeah.
And so then you do the 3,000 minus 700, and then with proper sig figs, 2,000 joules is the answer there. Okay? Again, it's base 1 plus base 2 divided by 2. So let's say this is base 1, right? That's from 10 to 15, that's 5. Okay? And this one is from 13 and a half to 11 and a half, so you gotta subtract those. And then add your two bases together, divide by 2, and then your height's what, negative 200? Okay? So that's how that one works. That makes sense.
Oh, wait,
Okay. Moving on. This one's easy. At room temperature, an oxygen molecule with such and such mass typically has this much kinetic energy. How fast is it moving, right? Since they mentioned kinetic energy, what are you probably going to write down?
1 mv squared.
Okay, so the kinetic energy is equal to 1/2 mass times v squared. What did they want to know? The speed, this v term here, okay?
So I can multiply both sides by 2, divide by mass, take the square root. So the speed then is equal to 2 times the kinetic energy divided by the mass, take the square root. How many sig figs should your answer have?
3.
3.
Do we need to know like the escape velocity?
We're getting there.
How big is this stuff?
Y'all make me laugh.
How long is this stuff gonna be?
However long I want it to be.
Have you made it yet?
No.
You should leak the test.
Tim, you got a question or you got an answer?
Answer.
Oh my
Answer.
god.
Okay, hold on, Tim.
Sorry, sir.
That's okay. Giving some people inferiority complexes over here and wrapping heads with us.
483.
No.
484.
Alright. Let's let somebody else drive the class. Ryan, what'd you get?
483.16.
And how many sig figs do we want? 3, so what is it? 184. Oh, yes. Okay, yeah, 484 meters per second. That was easy. Number 7. Pretty much exactly like number 6, except using elastic potential energy. Do you remember the formula for that one? 1/2 kx squared, okay? It's going to be the same stuff, so I'm not going to do that. Number 8, escape velocity. Alright?
K is the spring constant, right?
Yep.
And then X is
The displacement of the spring from the equilibrium position. Alright, so find the escape velocity for an object on the surface of a planet that has a mass, capital M, and a radius, capital R. Ignore air resistance. Since we're ignoring air resistance, that means conservation of energy can be applied, right? So, let's say this is our planet right here, and the planet has this radius R, and we know it's got a mass of M, okay? And some object is going to be launched into space off of the surface of the planet. The 0 line is going to be infinity away. Everybody good with that? Since we're escaping the planet, that means we will never return. Okay, this object is not coming back down. It's going to go away, which means we're going to say one day it could reach the 0 line, right? So that means it's going to run out of energy at that point. Okay, so our final position then is going to be at the 0 line. The initial position will be at the surface of the planet. Mechanical energy initial equals mechanical energy final. What kind of energy does it have here?
None. That's the initial.
where you said no.
Potential.
It has energy.
Oh,
Because we are blasting it off the surface of the earth, right? It's got kinetic, right? So we have kinetic energy initial. What else does it have since it is some distance away from the 0 line? Okay, it's got universal gravitational potential energy. Okay? And what does it have at the end? What?
You said one
What?
day it's gonna hit
Kinetic
the 0 line?
energy.
What?
Kinetic.
Huh?
I don't know.
We said one day it's going to hit the 0 line, okay,
Oh,
and run out of energy, right?
Oh, no energy.
So nothing, okay? Alright, so now let's see, what was that question? What do they even want to know about this? Okay, what is the escape velocity, right? Okay, so let's expand both of these things here. What's this going to be?
1/2 mv squared.
Okay, 1/2 m, and we're going to say this is called the escape velocity, okay? Now, universal gravitational potential energy has its own formula, what's that going to be?
Sorry.
Is that the big G?
It's got- it's
It's
got-
like the big G times.
M1.
Negative G M1 2 divided by R.
10?
Yeah.
What?
Are you looking at this?
Yeah, no, right
Negative.
here.
Oh.
Oh, I swear, I thought if you didn't.
Yeah, y'all can have your notes out.
If you didn't have the notes, I was about to leave.
So
No,
you
you
need
didn't.
to know that, right? So negative big G, M1, M2 over R. This M is also which one of these? One, right? The mass of the small thing, right? The number 2 we say is going to be the mass of the big thing, okay?
Wait, what is G constant equal again?
6.67 times 10 to the negative 11.
We gotta memorize this.
Yeah. Alright, so now let's see here. I can take this and I can move it over to this side, right? Because I'm trying to find out this. Yeah? So, 1/2 m1 times the escape velocity squared equals, now this is positive, big G m1 m2 over r. M1s are on both sides, so that can go away. Now what? Multiply both sides by 2, that gets rid of that. So the escape velocity then is equal to the square root of 2 times big G times m2 over r, understanding that m2 is the mass of the planet itself, right? So that's just that big M. So I'm going to go ahead and just switch that out for that capital M there, so it's in terms of like the problem I had set up originally. Okay? And then did they give me actual values?
No, sir.
No.
Nope, so then that's it. That's the answer. Okay? So then number 9 says, by what factor would the escape velocity change if the mass of the planet were quadrupled and the radius was 1/16 that of its original? So we're going to set up a proportion statement, right? Question?
Okay, so couldn't you memorize that statement? Because wouldn't that be the same for them all? Like,
Is that universal?
So long as the mass is m and the radius is r. But if I said the mass is 2m and the radius is 3r, you know, then that would change that up a bit.
They like to hear my deals. He hasn't made the test yet.
All right, so this is our equation, right? And we can cancel out constants if we're going to set up a proportion statement. So I can say then that the escape velocity is proportional to, that goes away, so that's going to be the square root of m over the square root of r. M changes by a factor of 4, so that's square root of 4 over. R changes by a factor of 1/16. Square root of 4 is 2. Anybody know what the square root of 1/16 is?
1/4.
4th?
Yes.
So I can multiply the top and the bottom by 4, which means that our factor of change is 8.
oh, that's cool.
I really didn't understand like all what was going on there.
This is just our proportion statement. Go back and review your
So it's like in our
proportion
notes?
notes. Yeah, so you get rid of constants, put your proportion sign instead of an equal sign, leave the things that are going to change, plug in the amount by which they change, solve, and this is the factor of change that this will
Okay.
have.
That first chunk was just
Yeah, we're just kind of mirroring this without the constants. Alright? Good. Other questions about that? Okay. Well, that was fun. Okay. So, number 10. Roller coaster car may be represented by this little box here. I should say the car is, not chorus. The car is released from rest at a height h above the ground and slides along a frictionless track. The car encounters a loop of radius r at ground level as shown. Find the minimum height the car must start at so that the car can complete the loop safely. Okay, now we talked about this in class, And we said that there is like a major point in the ride there that determines whether you're going to be safe, whether you're going to make it to the end safely. Where is that point?
Top of the
Zero
top.
The top of the loop, right? This is the point of no return. If you can get past this point, you're going to be okay, all right? Since it's wanting the minimum height so that you can be safe, remember we said that something was going to happen right there at that point. What was the car going to do at that point?
Leave the track.
Contact.
It was going to lose contact with the track, and it was just going to glide across the top and then finally make contact again, right? So we need to draw a free body diagram of the cart when it's right there at the top of that loop, okay? And the top of that loop then is going to be our final position for energy purposes. So what is the free body diagram going to look like for the cart when it's at that place?
Just force of gravity.
Just force of gravity. Okay, so force of gravity is going to be acting downward. Okay? It says that it's a frictionless track, right? So if friction's not there, then what is true?
Mechanical energy initial equals mechanical energy final.
Very good. Conservation of energy can be applied. So what kind of energy does it have at the beginning?
Potential energy.
What kind of potential energy?
Gravitational.
Gravitational potential energy initial. It says that it is released from rest, so that means there's no kinetic energy there. And it's not touching a spring, so okay. Now, the energy that it has here. Let's talk about it for a second. Obviously, it's above the zero line, right? Is it moving anymore?
Yeah.
Yeah, otherwise you don't get to finish the ride ever, okay? Now, what's the velocity vector look like at that place?
Scared.
Don't be scared.
I'm gonna let
Say
Tim.
it, David,
I'm gonna let
say
Tim
it.
go.
Say it,
Say it.
It's going that way.
He's going to the left.
It's going to the left.
right? And so what kind of velocity would we maybe call that?
Negative.
Centrifugal.
Centrifugal.
Tangential velocity, okay? That is tangent to the circle. So we have tangential velocity, right? So that means that we're going to have gravitational potential energy final, and we're going to have kinetic energy final. So that's the final place, right? And now let's expand. So we've got m times g times h naught equals m times g times h final plus 1/2 m times v final squared, understanding that that v final is really tangential velocity. What do you notice? Everybody brought mass to the party, so that can go away. And our goal here, we've been tasked with finding the initial height, right? So how can I get that alone? Okay, divide by little g. So the initial height then is equal to the final height plus the tangential velocity squared over 2 times little g. Now let's talk. The final height here is in reference to the zero line. How high up is this? Yeah, 2r, okay? So I can say that an initial height is equal to 2 times big R plus, do you know what that velocity is?
You can find it out.
We can find it out. How can we find it out?
Multiply by G. Wait, what are you talking about?
Tangential velocity. How can we get that? Where have we ever seen that before?
Rotation. Rotation. I forgot.
Oh man. Okay, Tim?
That's centrifugal force.
The centripetal force, okay? Since the object is going through rotation, that means that there's a centripetal force, right? So, what axis is the force of gravity pointing in?
Y.
What?
In.
In axis, okay? So the centripetal force then is equal to mass times what? Which is?
BT squared over R.
Very good, okay? Bt squared over R And it is also equal to what?
mv squared over r.
We got that.
Sorry. Force of gravity.
Yeah, the sum of all the forces in that axis, right? And we said that by convention, any force that points inward has what sign? Positive, okay? Inward pointing forces are positive, outward pointing forces will be negative. Okay, so that's going to be Fg, which is mg. Now what should I do? Okay, so that means that mg equals m times vt squared over r. What can we do? Mass goes away. Now what?
Solve the
Which is,
12 point G times R.
okay? So Vt equals, or let's say Vt squared. We'll leave it squared because it's squared over here, okay? So Vt squared is going to be equal to little g times r. So now, right here, I'll plug that in. So I'll say g times r over 2 times little g. What can you do? Cancel the g's. So that's going to be 2r plus half of r. So what's that? 2 plus a half. 2.5 r. Okay? So 2.5 times r is the initial height. The initial height was 15 meters. What's up?
Wasn't the velocity squared tangent velocity?
Yeah. Tangential velocity squared
okay.
equals each other. Okay, so what's 2.5 times 15?
37.5.
And how many sig figs do we want?
3. 2.
That make sense? Sure. Yeah, I got it. So, y'all had the energy stuff, okay? This was what we forgot.
When you
You
get-
forgot your centripetal force
So
thing.
when you get tangential velocity, you just gotta remember to do Fn.
F net in the n axis, yeah. Alright, let's see. A SpaceX shuttle of that mass with a satellite communication system payload is shot vertically upward from the surface of the Earth. If the satellite is to be put into geosynchronous orbit at such and such distance above the surface of the Earth, what would the initial speed of the shuttle be? And then I give you some values. Alright, so let's say that's Earth. This is the Earth radius. The space shuttle is going to start at this point, and we'll say right here is geosynchronous orbit, okay? That means that we're going to move from the surface out to this place right here. I'm going to just, for right now, call that D, some distance away, okay? And our 0 line is going to be infinity away.
I thought the 0 would be the geo orbit. So that's our final.
Now, yes, Earth does have an atmosphere, which means that air resistance will play a huge factor in launches, okay? But we're going to ignore that. And if we do ignore it, then what is true?
Conservation.
Conservation of energy. All right. So, mechanical energy initial is equal to mechanical energy final. So what kind of energy does it have on the surface of the Earth when we are launching it into space?
Kinetic.
Okay, it has kinetic energy initial. What else? Universal gravitational potential energy. Okay. Universal gravitational potential energy. Now, looking at the end there, okay, the final point, what kind of energy is it going to have at the end?
Potential universal gravity.
Yeah, it's not going to reach the 0 line, so it's not going to run out of energy. It's going to be here, away from the 0 line. So there's still going to be universal gravitational potential energy, final. But since it's going to geosynchronous orbit, that means it's going to stay in that orbit forever, right? Okay? So as far as movement is concerned from the initial launch, it's not going any further that way, okay? So what kind of kinetic energy, well, let me rephrase that. What kind of energy is it going to have?
Universal gravitational.
It's only going to have that, right? We're not going to have any more kinetic energy from this blast off, right? There will be kinetic energy around the Earth, right? But that's because of the force of gravity supplying a centripetal force on the shuttle, right? Or on the satellite, whatever we're talking about. But because of our launch, it's going to run out of kinetic energy in that direction, okay? So that's all we're going to say. It's only going to have this, okay? All right, so let's play the game. 1/2 m times v initial squared plus, what's the formula for universal gravitational potential energy? You can
Big G
just say it.
times
Negative G
M1
M1 M2 divided by R.
You forgot that's negative, okay? Negative big G times M1, M2 over R equals, what's it going to be over here?
Negative G M1 M2 over R.
Very good. Okay, now let's see here. What kind of M is that? Which one is it? M1, okay? So that means everybody brought M1 to the party, so that can go away. Now let's talk about this right here for a second, because it's not just R, alright? When it was right here, it was this value. But now it's going to be here, so what is it?
R plus D.
R plus D, okay? So we need to put that in here, that this is going to be R plus D, okay?
Why don't we do that for the last time?
Because we said it went all the way to 0. Yeah. All right. Now let's see. What am I trying to find here? What is this supposed? What am I
Velocity,
wanting?
sir.
The velocity, right? I want this thing. Okay. So let's take this piece and move that over here. And then, of course, we'll multiply by 2. Do you see anything else we can do here?
Put it in square root.
Do you see anything
Oh,
else? we can-
2G.
Yeah, we can factor all of that out, right? So the initial velocity squared is equal to 2 times big G times M2 times, that'd leave us with 1 over R minus 1 over R plus D.
How would you factor out the negative G? How'd you get rid of that?
That's still here. I just pulled 2G and M2 out. That leaves us with 1 over R minus 1 over R plus D.
Yeah, but it went from like in parentheses negative big G, and then when you flip over one of them to the other side, they both.
Because if I pull this over here, that becomes positive, so that's this positive. This is still minus, so minus. That's,
Is the R plus D just because it's the final one?
yeah, because it is now an extra piece D away. Okay, so now you can take the square root of both sides. and now it's just a game of plugging in numbers. But it's a very careful game that must be played, okay? I advise you to do little tiny pieces, save them in your calculator along the way, and then build up, right? So I figure out what 1 over this stuff is, and then what's 1 over that stuff, then do my subtraction, and then multiply it by that stuff, and then take the square root, okay? So just do little pieces there. It gives you all your values for each of those things. Be careful for units, okay? You were given kilometers. Is that standard SI unit for distance? No. You need to change that to meters, okay? And when we get to the end of that, how many sig figs should your answer have?
3.
Nope.
4.
G is negative 6.67 times 10 to the 11.
6.67 times 10 to the negative.
What's that?
No, you said negative 6.67. I have video proof, you'll see too. What'd you get?
10,030. 10,300. Sorry.
2,300.
Sorry.
Why don't you make sure we say that with the right
52,000.
Yeah, that's right.
I figure
Yeah,
I'm off on that.
3,000, so.
So 1.030 times 10 to the 4th with the right sig figs.
10,300, but then you change it back.
Yeah, then you have to change it to the scientific notation so you can get the right sig figs. Okay. All right. Cool. So that means tonight, if you look at the answer key that I have online, this one I wrote that down wrong. So I'm not changing it.
Sir,
All right. Good question. Yes, sir.
where will that entry be?
Oh, it's on my Google Classroom deal, so maybe you can get the hookup on my Google.
Thank you, sir.
Any other questions? Okay.
Because I had the same mistake.
You got your phone?
What's in
That's where you made a mistake.
A constant force of blah 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 is applied tangentially to a wheel with a radius of something. The wheel has a moment of inertia of that and is initially at rest. What would be the angular speed of the wheel after such and such time? Okay, so here's the wheel, here's the force applied. We're going to say this wheel has that radius right there, okay? Since I'm applying a force at some distance away from the axis of rotation, what do you know to be true? What's that going to cause? Torque, okay? So, that's probably what I can use then, okay? So torque is equal to I times alpha. And we can say that the force of gravity acting on the wheel, that's where we'll stick the axis of rotation. What's the other torque net statement going to be? The sum of all the torques that are acting on the wheel, right? So what are all of the torques? The torque caused by the force applied. How do I find the sign of that torque? Right hand rule. So, put your right hand on the axis of rotation, point your fingers along the lever arm, bend in the direction of the force, and that's pointing into the board. What's that mean? Negative. Okay. And now what? Something equal. So we know that the torque caused by the force applied equals I times alpha. Since they asked me for the angular speed, in other words the angular velocity, I should probably go for the only thing that has anything to do with angular stuff in the problem, right? So what can I do over here? Expand, right?
Oh, yeah.
So what's that going to be?
Negative force applied times D times sine theta.
Okay, negative F d sine theta equals I times alpha.
Isn't alpha tangential velocity squared root?
No, we don't want tangential velocity, we want angular velocity. Something.
So we just
This right here, what's that gonna go to?
Oh,
What's the angle between the lever arm and the force vector? 90, what's the sine of 90? 1, so then this we can just ignore, right? Let's go ahead and divide by moments of inertia on both sides. So that means alpha is equal to force applied times d over I. So you can plug that in. Now let's see. Angular velocity is equal to, what do you think?
do you need to look that
it's
up?
omega. Is it?
Nah.
Change it to omega.
Omega over radius. Omega
Okay.
over theta. Something like that.
Let's just inspect the thing. We know it, we're going to have to use this, right? Because that's the only angular thing I know. That's in units of radians per second squared, right? And I need it to become just radians per second.
Or we just
How can I turn this into this?
take the square root.
What?
Divided by 10.
This is in the denominator. Multiply. So if I multiply that by time, then that will cancel out and I'll get this, right? So that means alpha times time. And they gave me time in the problem. That's delightful, right? So I'm going to say this is alpha. Okay, so negative force applied times d over I times time. Now, let's talk about this right here. Since they asked me for the angular speed, this right here would be telling me whether this velocity was clockwise or counterclockwise, direction and stuff. Do they want to know that? No, so I'm going to go ahead and just ignore that now. Okay?
Put it in right form.
Get so confident when you realize it's gonna be wrong.
You're wrong.
So you're doing 2 steps, right? So you're stupid, I'm right. That's in 1 sig fig.
That's two.
It has to be in 2 stupid.
That's one secret.
No, it's not here.
Yeah.
Right.
Alright. Hey, you can already get
I'm going to solve for one of the things that's changing.
Oh, that's the number.
Right. Okay.
No.
Okay.
It's true.
That one's really easy. Solve 13.
Oh, can we just skip
Oh,
it and then?
No,
Skip
no,
it, yeah.
no.
No,
I need to
no,
figure out
no,
if I can. If I
I
can't
don't
do
wanna
this,
skip
I'm
it.
not coming
If
on.
it's easy. No, 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 no.
You have to make it on Thursday.
Yes, okay.
What?
I will be up on it anyways, and then we'll figure this out now.
Oh, you have to
Wait,
know
what?
the
Special.
Yeah, I told you you have to know that one.
I mean, once I know that, this problem's easy. If
Yeah.
I don't, it's gonna be hard.
Remember, I told you must know the moments of inertia of a point mass, okay? So please figure out what that is.
Are we gonna have that chart?
Huh?
Are we gonna have the chart that? Probably not, because.
You'll have it for, or I will write in the moments of inertia for anything that you need, okay? Except for point mass, you'll have to know that one. Alright, so we know that the moment of inertia for a point mass is mr squared. You know the mass of the ball. The axis of rotation is here. The ball's gonna swing around, right? So that means that r is gonna be the length of that piece of string. So that's very easy. The reason that it says that it is a, what does it say, a light wire, okay? That means that wire is massless. You don't figure that into the moment of inertia.
Oh, this is solid. Is moment of inertia a negative number?
M r squared. What's the unit for m?
Kilogram.
What's the unit for r squared?
Meters squared.
So what's the unit for moment of inertia?
Kilogram squared.
There you go.
Seriously?
Number 14. A certain drive shaft has a rotational kinetic energy of 15 kilojoules and rotates with an angular velocity of 75 radians per second. What is the moment of inertia of this drive shaft? Alright, so that says rotational kinetic energy. What's the formula for rotational kinetic energy?
Oh,
What'd you say? Okay, 1/2 I times omega squared. And I want to know this, right? So what do? Multiply by 2, divide by omega squared, and then that's it, right? So I equals 2 times the kinetic energy divided by angular velocity squared. So that's easy. Let's move on. A hoop with an axis of rotation through its center rolls down an inclined plane. What is the fraction of its kinetic energy that comes from its rotation? Okay, so axis of rotation through the middle of the hoop there, okay? There's a force down the plane that acts on the center of mass of the hoop, and then the hoop touches the inclined plane, and it says that it rolls down, which means that we would have static friction here. That static friction is some distance r away from the center of mass of the hoop, which means the static friction is causing the torque that makes the hoop roll and makes it go down to the bottom. And this is acting on the axis of rotation, so that generates no torque at all, right? Now, if this is our 0 line, and the hoop ends up down here, and it started up here, we can talk energy, okay? So let's say mechanical energy initial equals mechanical energy final, and then up here it's some height above the 0 line, so it's got gravitational potential energy initial. And say starts from rest. Okay, we're going to say it starts from rest. Equals, it's going to have translational kinetic energy final, and it's going to have rotational kinetic energy final when it gets to this point, right? So that's mg h naught equals 1/2 mv final squared plus 1/2 I omega squared. I need to know what I is, and I need to know what omega is. Omega is Vt over R, right? What's I for a hoop? Do you have your moment of inertia sheet?
No, you said this we only had to know the temper.
Yeah, but it's not your test. This is just a test for you.
Oh. Get out your worksheet and tell me what the moment of inertia is.
We need to.
No, you don't.
Where's your page?
I don't have it.
Oh, I promise.
I'm pretty sure
I know, yeah.
it's Kimber.
Yeah, no, dude.
Anyone have their page?
Very bad time.
I know exactly what it is.
Yeah,
Hoop is mr squared.
There you go. Alright.
Same thing.
Uh-huh. So, our moment of inertia for the hoop is going to be mr squared. So we're going to get m times g times h naught equals 1/2 m times v final squared plus 1/2 times mr squared times vt squared over r squared. So let's see here. Everybody brought mass to the party, so that goes away. If I multiply this times this, then these go away. So I have g times h naught equals 1/2 v final squared plus 1/2 v tangential squared. This was the rotational energy part here, and I have two pieces. Half of the energy at the end comes from its rotational kinetic energy. Okay? So this is the fraction from rotational kinetic energy.
Can you explain that again? So,
The question
Yeah, the question asks for the fraction. So all of the beginning energy is split into these two things here, and half of it is going to be from the translational, and half of it is going to be from rotational.
Okay.
Okay?
So even if those two, like, let's say this number is like 3 and 2, it would still be 1/2, right? Because it would split into two parts.
If this was like 3/4 and that was 1/4, then the answer would be 1/4.
Okay, I got it.
Wait, over, like your second, like you know how you did it. I know.
Oh,
Okay,
then
so
I
it says
get
like VT squared over, is that over R squared?
Uh-huh.
And then, so you got that from the W, yeah, from there. But then, how did you include the R being squared?
Omega squared, so if
Oh,
this
so
is
you're
squared,
squaring
then
that.
everything else is squared.
Okay, and, okay.
Okay?
that should be fine.
Alright. Are we getting close to the end?
Yeah, we agree more.
Y'all want to do all three, or?
That's
Yes.
Okay.
I need it.
Dinner break.
Hey,
I need
if
that.
you're not in it, you can leave.
Alright.
Awesome.
Alright, so to weigh a fish, a person hangs a tackle box of mass 3.5 kilograms and a cooler of mass 5 kilograms from the ends of a uniform rigid pole that is suspended by a rope attached to its center. The system balances when the fish lands at a point 1/4 of the rod's length from the tackle box. What is the approximate mass of the fish? Okay, so this is a system in static equilibrium, right? It's not moving. So that means we got two pieces here. What are those two pieces?
Translational
Translational and
and rotational.
rotational, okay? So in the translational system, that means we're going to have to do a free body diagram, right? Okay, so there's a mass, force of gravity. That has a mass, force of gravity. The pole, let's see, attached to its center. Does it give me a mass of the pole?
No.
No? Okay, so well normally that would act at its center, but we'll ignore it this time. That has a mass, force of gravity, right? And the rope, force of tension pointing up. So that's our free body diagram. Okay, so that means F net in the y-axis is equal to mass times the acceleration in the y-axis. And since this is in equilibrium, what is that?
0.
0.
Force, tension,
Newtons, thank you. Oh dear. Alright. F net in the y-axis is equal to the sum of all the forces in the y-axis, so that's going to be the tension force from the rope minus the force of gravity because of the tackle box, minus the force of gravity because of the cooler, minus the force of gravity because of the fish. Okay?
You're not in it.
So now what am I going to do? Set them equal. Alright, so force of tension minus force of gravity of the tackle box minus force of gravity because of the cooler minus the force of gravity because of the fish all equals 0. And we're supposed to be trying to find the fish here, okay? But before I do any more work, can I know what this is since I have the mass of the tackle box? Can I know what this is since I have the mass of the cooler? Do I know what this is?
No.
I don't. Do I know, or can I know this? Nope. So I have two unknowns, which means I can't go any further with translational, right? Move to rotational. What do you have to do rotational? Very good.
Are we ever gonna get a problem where we can just use translation?
Alright, so where would you like the axis of rotation to be here?
I'm trying to find the force of tension, so let's put it on
We
the
must
fish.
You are not trying to find the force of tension. You are trying to find the mass of the fish.
We want it to be one of the
You do want it to be one of the unknowns.
So put it at force of tension.
Yeah, let's put it right there and that gets rid of that. We don't even have to mess with it.
Yay.
Okay, so the torque net then, when the tension force is at the axis of rotation, is equal to what? I times alpha. And since this is in equilibrium, what is that?
0. Newtons.
Ah,
No, Newton meters.
Newton meters.
Sorry.
Alright, and then torque net when the tension force is at the axis of rotation is equal to what else? The sum of all the torques, right? So there's a torque that's going to be caused by the force of gravity on the tackle box. And there's a torque that's going to be caused by the force of gravity on the fish. And there's a torque caused by the force of gravity on the cooler. Right? What do I need to do now? Right hand rule, okay? So I'm going to put my right hand at the axis of rotation, point my finger along the lever arm, bend in the direction of the force applied. What's the sign for this one? What's the sign for this one? What's the sign for this one?
Negative.
Negative. Okay.
So the tackle box is negative.
Which one's the 5 kilogram one? That's the cooler.
cooler.
Okay? So minus and plus. Alright? Now what? Set them equal. So, the torque because of the tackle box plus the torque because of the fish minus the torque because of the cooler equals 0 Newton meters. What's the thing I want to know about? The fish. So I'm going to isolate this torque, right? So I'm going to move this one over here, and I'm going to move this one over here. Okay? So the torque caused by the fish is equal to the torque caused by the cooler minus the torque caused by the tackle box. Now what? Span. So what's that going to be? What is the formula for torque? Sine. Fd sine theta. Now this F is a force of gravity, right? Which has its own formula, which is m times g. So that means we're going to say the mass of the fish times little g, that's force, times d, the lever arm out to the fish, right? Let's see here. If this is the axis of rotation, and here's the location of the fish, that means the fish is located L/4 away, right? The entire length divided by 4 away. Now, the angle, here's the lever arm, here's the force. What's the angle between them? 90. Sine of 90 is, so we'll ignore that piece, equals, okay, let's play the game over here now. This one is going to be the mass of the cooler times little g times the lever arm out to the cooler, right? The cooler is the 5 kilogram one, so that's going to be L/2 away. And the angle is still 9, so we'll ignore that. Minus the mass of the tackle box times little g times that lever arm, that is L/2 away. Everybody brought g to the party, so that can go. I want this, so I'm going to multiply by the reciprocal here, 4/L. Which means I got L on top and bottom, and that goes away, and 4 divided by 2 is 2. So that's going to be 2 times the mass of the cooler, minus, again, L's go away, that's 2, so 2 times the mass of the tackle box, and that goes away, so mass of the fish then is this. Alright, so let's see, that's going to be 2 times 3.5 minus 2 times 5. Did I say them backwards? Yeah. Yeah, okay. Mass of the cooler is 5. So 2 times 5 minus 2 times 3.5. Or we could even factor that out even more and say, pull a 2 out. 2 times mass of the cooler minus mass of the tackle box. So what do you get?
3 kilograms.
Yeah.
3 kilograms. How many sig figs are you supposed to have? 1. What? Is that really one? Yeah. Okay.
So why did you have to leave this stuff on the translation?
Well, first off, you had to see if maybe you could get the answer with translational, and secondly, without doing this, you don't know where you want to put your axis of rotation, because you wouldn't outright know what your unknown is. It's a good way of determining, oh, I don't know this, and I don't know that. Where do I want to put my axis of rotation? If you can see past all of that, then don't do it. Alright, any questions about that? Okay, understand that I asked you for the mass, right? If I asked you for the weight of the fish in newtons, okay, then you would have left the g, right? You'd be solving for mg, or the force.
Or can you just multiply that number by 9.8?
You should.
Okay.
one is exactly like the one out of your notes. Do I really need to go through this one? No, this, again, this is that one that looks like this. Right, okay, and so you have a rotational part of it, you have a translational part of it, okay? When you did your free body diagram on the disc, right, we looked at it from top view, from above, so we had our tension force like this, right? Y'all remember that? Okay, so since this is some distance away from the axis of rotation, this force is going to cause a torque on the disc. It's going to cause it to turn, okay? The acceleration was down, so we remember the key to the problem here is make that negative AY when we do our F-net statements, okay? And then here we are going to do our torque net statements, and then we can solve for all of those things. Remember, at some point, we'll find out that the tangential acceleration around the disk is equal to the AY, so we just rename it A. Y'all remember that? The tension here is the same as the tension there. And we know that, let's see, what is it? Alpha is equal to tangential acceleration over R. Isn't that right? I think that's right. So if you figure out what this is, then you can figure out what that is, right? So we don't need to mess with that problem. That's easy. Alright, let's look at this very last one. Okay, an engine maintains constant power on a conveyor belt machine. If the belt's velocity is tripled, the magnitude of its average acceleration is what? Alright, well we know that power is equal to work over time, right? The rate at which work is done. Work is equal to force times displacement times cosine of theta. Distance over time is velocity, so that's force times velocity times cosine of theta. So, power is equal to force times velocity times the cosine of theta. Let's solve for something that's going to be changing, alright? Let's solve for force, okay? You could solve for either one, it doesn't matter, I just pick force. Alright, so force is going to be equal to power over velocity. I'm going to ignore this right here because we're going to make a proportion statement in a moment, and the cosine of an angle is a constant as well. So I'm just going to ignore that because it's a constant, alright? It said in the problem that we're going to maintain constant power, right? Which means that this goes away. So that means that force is proportional to 1 over the velocity. But they didn't ask me about the velocity, they asked me about the acceleration. Given the things that I know, what can we say that involves acceleration and that will help me in this problem? What else do I know? It's got to have acceleration in it, and it's going to have one or both of those in it. We pretty much spent this entire cram session using the formula that we need to use here. It's like the most used formula in all of physics.
Half mv squared.
What?
Half mv squared.
No. It's Newton's second law. Oh, interesting. Okay, so force equals mass times acceleration. So that contains one of the things I want and one of the things I know, right? Okay? Anything that I put on that conveyor belt is going to stay the same mass the whole time, right? So that means that this is constant, which means that force is proportional to the acceleration. That means I can swap them out and won't change anything, right? that means that acceleration is proportional to 1 over the velocity. It says that the velocity is tripled. So I put a 3 in place of velocity. So what happens to the acceleration then? Drops by 1/3, right? Okay, the acceleration is reduced by 1/3. Yay! Good job. Successful cram session.
Great.
Thank you, Mr. You're welcome.